Okay, this is the second step in the Lincoln Park Pavilion, step 01. In the previous step, we went ahead and used a similar operation as flow along surface in Rhino to project these curves from a base surface onto the barrel vaulted surface. And then we went ahead and mirror them and isolated the inside curves. So what we want to do to start with that is this step is going to be all about creating the onion domes. And as we kind of mentioned in the example, the first set doesn't have an onion dome. So we're actually, of the 5 potential bays here, we're only going to be putting onion domes in the second, third, and fourth bay here. Okay. In order to do this, what we need to do is isolate these bays by finding the intersection point of where the bays come together and kind of isolate the curves between those bays. And to do that, we need to first start with these 2 inside curves. We did that in the last step by doing a list item and isolating the inside of each of those. So let's go ahead and bring those down. So again, that's a simple geometry and curve component. And geometry parameters curve, and I'm going to call this inside curve A. And we're going to go ahead and make this a wireless receiver. And we're going to do the same thing, but call this one inside curve B. And we're going to rewire it like so. And be sure to turn off this old data for this entire step. And there we go, and bring these down below. Okay, so what we need to do is find the intersection point where curve A and curve B actually intersect. To do that, we're going to go underneath our intersect tab, and because these are 2 physical things, they're actually curves, we're going to go underneath the physical tab and go to curve and curve, and that will help find us the intersection of 2 curves. We run A into A, B into B, and there we go. It's very specific. It finds, the first point, second, third, and each of these is at the exact middle point of the individual bays. So what we want to do then is shatter these longer curves at those locations so that we essentially break these long curves into subcurves that are at each of those bays. So again, underneath curve, division, and shatter. We're going to use 2 of these. You'll see that T sub A and T sub B are what we're going to be focusing on. You can find the actual points themselves. All 6 of these points are coming out of that P output, and that P output is again the XYZ location of those 6 points. But then the T sub A is the length along curve A where you can find each of those points, okay? And then the T sub B is the location along curve B where you can find each of those points. And because they are exact mirror images of each other, they should be identical. But we will use A to A and B to B just to be the same about it. Let's go ahead and delete that, and we're going to go ahead and run A into the T sub A into the little t of shatter, the top shatter, and then obviously run the shattered curve A into the C input of that first shatter. And we're going to do the same thing, but kind of opposite for the B. And so now if we kind of start turning a couple of these things off, nothing looks like it changed, but if you actually go into the shatter, you'll see you've got 5 versions of shattered curve A and 5 shattered versions of curve B instead of 1 long curve like so. Okay. From there, what we want to do is we need to essentially isolate. We're only focused on the second, third, and fourth, or I guess what you could say is index number 1, 2, and 3. Okay, because we don't care about the first bay and we don't care about the last bay in terms of making the kind of onion dome forms. So what we want to do, this could change. So we want to make this parametric. We don't just want to say, let's eliminate bay 0, keep bay 1, 2, and 3, eliminate bay 4, because in theory we could come back here, change this geometry, and then the number of bays would alter. So we want to say, all right, we want to count the number of bays there are. We want to eliminate the first and the last one, okay? So what we're going to do is we're going to go ahead and count either the shattered curve A's or curve B's, doesn't matter. So we're going to underneath our sets, list, and list length. And that will tell us, how many curves there are. There are 5 curves in this location, okay? Then what we want to do is we want to create a domain. We want to say we want to keep bays blank through bay blank. In this case, bay 1, because again, index 0 is the first bay, we don't want that, bay 1, through whatever this list length is, minus 1, okay? So we want to create a domain, so again, go underneath math, domain, construct a domain. We know that we're always going to start at domain 1, not at domain 0, so we're going to put a panel tool in there and put a value of 1 in there, okay? We're always eliminating the very first bay, which is index number 0, so we want to start at 1. And then what we want to do is we want to say, all right, however many are in here, we want to subtract 1. So we're going to go and right-click on the B input, go to expression, and type in x minus 1. And that will say, all right, we have 5 right now. We're going to do 5 minus 1. So we want to go ahead and keep bays 1 to 4. So 1, 2, and 3. Now that doesn't make sense, okay, because we actually have 1 less. So even though we have 5 bays here, because the index numbers, it only goes to index number 4. So we actually have to subtract 2. So we got to go back in here, change our expression, and now it's x minus 2. Now that will say, there we go, items 1 to 3. Let me just put a panel tool in there. We want to keep 1 to 3. Again, we had 5 bays, but that means index number 4 is the last bay. So we need to subtract 2 from that to get to index number 3 so that our domain reads 1 to 3. Perfect, okay? The reason we want to construct a domain is because we want to use a new component called sets list and a sublist. So it's saying which of these curves do we want to keep, or which of the curves from shattered set A do we want to keep. We want to keep 1 to 3. And there we go. We're going to do the same operation, copy and paste this down below, but this time we're going to use the second shattered. And there we are. So now if I go ahead and turn off some of this previous information, and I'm going to go ahead and just group this while we're here. There we go. You'll see that it eliminated the first bay and it eliminated the last bay. We're only focusing on bays 1, 2, and 3 now. So now what we want to do is we need to create, let me go back to our images. We need to create, we've isolated these bays. We need to be able to create these seams to loft through. It's essentially kind of a revolution, but it's not a true revolution because if you revolve this, you get a perfectly smooth, half cylindrical-like shape, half kind of bulb-like shape, what have you. What we want to do is we want to take this edge curve, we want to rotate it to the midway point so it stands upright. We want to rotate it to the quarter point and the 3/4 point and revolve all 5 of those. The starting one, the quarter, the half, the 3/4, and the end. The other important thing to note, though, is that they're not perfectly flat, and I'll talk about that here in just a second. So when I say they're not perfectly flat, you'll see that these curves all move in 2 directions. Let me go ahead and just isolate the A's right there. It's actually more difficult to see when they're green. But you'll see that because they are flowing along the curve, they're actually arced. So we need to flatten those out. So what we want to do is we need to go ahead and find the axis to revolve around. So essentially we want to create a line from the starting point of the first bay to the end point of the first bay. So we'll take either of these curves. It doesn't matter if you take the A's or the B's. We want to find the starting and the end points. So again, we're going to go underneath the curve, analysis, and endpoints. We're going to run the curves into there, and now we get the starting and the end points of each of those. And we just want to simply draw a line through those. So again, curve, primitive, and line. And just draw a line from the starting to the end point like so. And now you get this line that's going to act as a revolution axis, if you will. And you'll also see what I mean by when I say that these curves are not flat. Okay? So from there, what we want to do is we need to go ahead and find what is the angle that these curves are relative to this flat line, this plane, if you will, that line could be passing through. Okay? So we want to find the midpoint of all 3 of these curves, the A curve, the B curve, and that axis curve that we just generated. To find the midpoints, we're just going to go underneath our curve, analysis, and point on curve. We're going to make 3 of these. Notice it's already set at the halfway point, 0.5. And remember, what this does is it automatically reparametizes all these items. So we're going to find the midpoint of the curve we just generated, the line between them. We're going to find the midpoint of the curve A's and the midpoint of the curve B's. Okay? Now we need to figure out what this angle is between these 3 points, between the midpoint of curve A, the midpoint of the center axis, and the midpoint of curve B. Okay? To do that, we need to create 2 vectors. We can measure the angle between 2 vectors. So if we go underneath vector, vector, and angle, we can measure the angle between 2 vectors, but we need 2 vectors. So our first vector is going to go from the midpoint of the center curve to the midpoint of curve A. And then we're going to create a second vector that goes from the midpoint of the center curve to the midpoint of curve B. So again, vector, and this point in time we're going to do a 2-point vector. And again, it's going to go from the midpoint of the center curve, which is this midpoint of the line. That's always going to be the A. And then we're going to go into the midpoint of curve A. That goes into B. Now remember, you can't see vectors, okay? But we can display them in case you're kind of curious what it looks like. Go underneath your display tab, vector, and vector display. You run your vector into the V, and whatever you have going into your A of your vector should also go into the A, which is the anchor point of your display vector. So that's the midpoint of the center line. And there you go, you can see that vector that we just constructed. I'll go underneath here, it's a little easier to see. It goes from the middle axis to the midpoint of the curve A's. And you'll see we've actually done it 3 times. We've done it for each of the bays, and there we go. We want to construct the same exact vector, but instead of the B, we're going to unwire the B. And we're going to use the midpoint of curve B's as the new B. And again, if you want to see this one, okay, again, the A is the same center or the same anchor point, and there's your new display vector. Okay, so you can now see that, and we can now measure the angle between these 2 vectors. Notice that it's not flat, so it's not going to be a perfect 180-degree revolution. It's going to be a little bit less than that. So we want to go ahead and find the angle between vector A and vector B. That always displays in radians. Okay, notice that each one is actually slightly different. There it is. Okay, the 2 outside ones are pretty much identical, and the inside one is slightly different. And we can change this by right-clicking, and we can actually convert this to, at least I thought used to be able to convert it to degrees. Doesn't look like we can, but what we can do is use the degree component. So go underneath math, go to trig, and we're going to do the degrees. Okay, so this will convert an angle specified in radians to degrees for us. There you go. So we have it now set up for a little bit less than, it's a little bit less than 180, okay? But this way it'll be exact for based off of each of our individual bays within here. So perfect. Let's go ahead and just, let's isolate some of these guys. I'm going to pull these guys down a little bit, and we're going to just group all of this stuff and turn it off. Okay. And we may leave our vector displays on just to be able to visualize those a little bit easier, like so. All right, so the last thing we need to do is we want to go ahead and create a range of rotation angles within there. So we want to go ahead and take those. We want to go ahead and take our individual degrees. Okay, we want to create 4 different rotation angles, okay, because we want to go from the 0, the 25, the 50, and the 75, okay. So what we're going to do is we're going to create a range of points. So go to Sets, Sequence, and Range. The D is the actual range of degrees that we want, so we're going to run our degrees into that range. The N is the number of different steps that we have. So again, the 0, 25, 50, 75, and 100. So we want to create 4 of those. So you'll see when we create 4 of those, it actually creates a starting one, which is a 0, and an ending one, which is the 100%, and it creates 5 resulting values. Okay, so again, when we only put 4 in there, it actually gives us the first one and the last one, but it gives us our 3 interstitial ones. We want the 25%, the 50%, the 75%. Of this, we don't care again about the first one and the last one. Technically, we already have those curves. Remember, these are our rotation angles. So what we want to do is we want to eliminate the first one and the last one. To eliminate, we want to go ahead and cull. So we're going to go underneath our sets, sequence, and cull index. Okay. So what we want to cull is index number 0, because we don't want the first one, and index number 4. So parameters, I'm going to put a panel tool in here. I'm going to put the value of 0, enter 4. Do not hit space, do not hit enter after the last 4. Just do exactly what I said. 0, enter 4. Click off of it, and remember, we can't just feed this in there because it doesn't understand that as separate integers, separate values. It thinks it is one continuous value, and there is no 0 space 4. So what we want to do is right-click and do multi-line data. So it puts each of those entries as its own individual entry, and that will work just the way you want it to. And now you'll see what it's done is it's eliminated the first and the last, keeping only the middle 3. There we go. So that's exactly what we want. Is now we've got the 25%, the 50%, and the 75% rotation marks, degree marks, if you will. So let's go ahead and from there we'll pause again on this video. I'm going to group this last one. Take a moment, go ahead and annotate that entire second step, and we'll continue with the third step in just a moment.